Ethylene oxide, properly called oxirane by IUPAC, is the organic compound with the formula C2H4O. It is a cyclic ether. Ethylene oxide is a colorless flammable gas at room temperature, with a faintly sweet odor. It is the simplest epoxide, a three-membered ring consisting of one oxygen atom and two carbon atoms. Because of its special molecular structure, ethylene oxide easily participates in addition reactions, e.g., opening its ring and thus easily polymerizing. Ethylene oxide is isomeric with acetaldehyde and with vinyl alcohol, although it is a vital raw material with diverse applications, including the manufacture of products like polysorbate 20 and polyethylene glycol that are often more effective and less toxic than alternative materials. Ethylene oxide itself is a very hazardous substance. At room temperature it is a flammable, carcinogenic, mutagenic, irritating, and anesthetic gas, with a misleadingly pleasant aroma. The chemical reactivity that is responsible for many of ethylene oxide's hazards has also made it a key industrial chemical, although too dangerous for direct household use and generally unfamiliar to consumers. Ethylene oxide is used industrially for making many consumer products as well as non-consumer chemicals and intermediates. Ethylene oxide is important or critical to the production of detergents, thickeners, solvents, plastics, and various organic chemicals such as ethylene glycol, ethanolamines, simple and complex glycols, polyglycol ethers and other compounds. As a poison gas that leaves no residue on items it contacts. Pure ethylene oxide is a disinfectant that is widely used in hospitals and the medical equipment industry to replace steam in the sterilization of heat-sensitive tools and equipment, such as disposable plastic syringes. Ethylene oxide is industrially produced by direct oxidation of ethylene in the presence of silver catalyst. It is extremely flammable and explosive and is used as a main component of thermobaric weapons. Therefore, it is commonly handled and shipped as a refrigerated liquid. History. Ethylene oxide was first reported in 1859 by the French chemist Charles-Adolphe Wurtz, who prepared it by treating 2-chloroethanol with potassium hydroxide, ClCH2CH2OH plus CoO plus KCl plus H2O. Wurtz measured the boiling point of ethylene oxide as 13.5 degrees Celsius, slightly higher than the present value, and discovered the ability of ethylene oxide to react with acids and salts of metals. Wurtz mistakenly assumed that ethylene oxide has the properties of an organic base. This misconception persisted until 1896 when Georg Bredock found that ethylene oxide is not an electrolyte, that it differed from other ethers, particularly by its propensity to engage in addition reactions, which are typical of unsaturated compounds, had long been a matter of debate. The heterocyclic triangular structure of ethylene oxide was proposed by 1868 or earlier. Wurtz's 1859 synthesis long remained the only method of preparing ethylene oxide, despite numerous attempts, including by Wurtz himself, to produce ethylene oxide directly from ethylene. Only in 1931 did French chemist Théodore Lefort develop a method of direct oxidation of ethylene in the presence of silver catalyst. Since 1940, almost all industrial production of ethylene oxide has relied on this process. Sterilization by ethylene oxide for the preservation of spices was patented in 1938 by the American chemist Lloyd Hall. Ethylene oxide achieved industrial importance during World War I as a precursor to both the coolant ethylene glycol and the chemical weapon mustard gas. Molecular structure and properties. The epoxy cycle of ethylene oxide is an almost regular triangle with bond angles of about 60 degrees and a significant angular strain corresponding to the energy of 105 kJ per mole. For comparison, in alcohols the COH angle is about 110 degrees, in ethers, the COC angle is 120 degrees. The moment of inertia about the principal axes are Ia equals 32.921 times 10⁻40 grams cm squared, Ib equals 37.926 times 10⁻40 grams cm squared, and Ic equals 59.510 times 10⁻40 grams cm squared. The dipole moment at a temperature in the range 17 to 176 degrees Celsius is 6.26 times 10⁻30 cm. The relative instability of the carbon-oxygen bonds in the molecule is revealed by the comparison in the table of the energy required to break two CO bonds in the ethylene oxide or one CO bond in ethanol and dimethyl ether. This instability determines the chemical activity of ethylene oxide and explains the ease of opening its cycle in addition reactions. Physical properties. Ethylene oxide is a colorless gas at 25 degrees Celsius and is a mobile liquid at 0 degrees Celsius. Viscosity of liquid ethylene oxide at 0 degrees Celsius is about 5.5 times lower than that of water. The gas has a characteristic sweet odor of ether, noticeable when its concentration in air exceeds 500 ppm. Ethylene oxide is readily soluble in water, ethanol, diethyl ether and many organic solvents. Main thermodynamical constants are standard molar heat capacity, Cp degree equals 48.19 J. Standard enthalpy of formation, delta H degree 298 equals minus 51.037 kilojoules per mole. Standard entropy, S degree 298 equals 243.4 J. Gibbs free energy, delta G degree 298 equals minus 11.68 kilojoules per mole. Heat of combustion, delta Hc degree equals minus 1306 kilojoules per mole. The surface tension of liquid ethylene oxide, at the interface with its own steam, is 35.8 millijoules per square meter at minus 50.1 degrees Celsius and 27.6 millijoules per square meter at minus 0.1 degrees Celsius. The boiling point increases with the vapor pressure as follows: 57.7, 83.6 and 114.0. Viscosity decreases with temperature with the values of 0.577 kilopascals S at minus 49.8 degrees Celsius, 0.488 kilopascals S at minus 38.2 degrees Celsius, 0.394 kilopascals S at minus 21.0 degrees Celsius and 0.320 kilopascals S at 0 degrees Celsius. Between minus 91 degrees Celsius and 10.5 degrees Celsius, vapor pressure P varies with temperature as LGP equals 6.251 1115.1. *N. A. Data not available. *N. A. Data not available. Chemical properties. Ethylene oxide readily reacts with diverse compounds with opening of the ring. Its typical reactions are with nucleophiles which proceed via the SN2 mechanism both in acidic and alkaline media. The general reaction scheme is, and more specific reactions are described below. Addition of water and alcohols. Aqueous solutions of ethylene oxide are rather stable and can exist for a long time without any noticeable chemical reaction. But adding a small amount of acid, such as strongly diluted sulfuric acid, immediately leads to the formation of ethylene glycol, even at room temperature. O plus H2O CH2CH2OH. The reaction also occurs in the gas phase, in the presence of the phosphoric acid salt as a catalyst. The reaction is usually carried out at about 60 degrees Celsius with a large excess of water, in order to prevent the reaction of the formed ethylene glycol with ethylene oxide that would form di- and triethylene glycol. 2O plus H2O CH2CH2OCH2CH2OH. 3O plus H2O CH2CH2OCH2CH2OCH2CH2 H2OH. The use of alkaline catalysts may lead to the formation of polyethylene glycol. NO plus H2OH. Reactions with alcohols proceed similarly, yielding ethylene glycol ethers. O plus C2H5OH HOCH2CH2OC2H52O plus C2H5OH HOCH2OCH2CH2OC2H5. Reactions with lower alcohols occur less actively than with water and require more severe conditions, such as heating to 160 degrees Celsius and pressurizing to 3 megapascals and adding an acid or alkali catalyst. Reactions of ethylene oxide with fatty alcohols proceed in the presence of sodium metal, sodium hydroxide or boron trifluoride, and are used for the synthesis of surfactants, addition of carboxylic acids and their derivatives. Reactions of ethylene oxide with carboxylic acids in the presence of a catalyst results in incomplete, and with anhydrides, incomplete glycol esters. O plus CH3COOH HOCH2CH2OCOCH3O plus 2OCH3COOCH2CH2OCOCH3. The addition of acid amides proceeds similarly. O plus CH3CONH2 HOCH2CH2NHCOCH3. Addition of ethylene oxide to higher carboxylic acids is carried out at elevated temperatures and pressure in an inert atmosphere. In presence of an alkaline catalyst, such as hydroxide or carbonate of sodium or potassium, the carboxylate ion acts as nucleophile in the reaction. RCOOH plus O minus RCOO minus plus H2OO plus RCOO minus RCOO CH2CH2O minus RCOO CH2CH2O minus plus RCOOH RCOO CH2CH2OH plus RCOO minus. Adding ammonia and amines. Ethylene oxide reacts with ammonia, forming a mixture of mono, di and triethanolamines. The reaction is stimulated by adding a small amount of water. O plus NH3 HOCH2CH2NH22O plus NH32NH3O plus NH33N. Similarly proceed the reactions with primary and secondary amines. O plus RNH2 HOCH2CH2NHRD. Alkylaminoethanols can further react with ethylene oxide, forming amino polyethylene glycols. NO plus R2NCH2CH2OH R2NCH2CH2ONH. Trimethylamine reacts with ethylene oxide in the presence of water, forming choline. O plus 3N plus H2O HOCH2CH2N3 plus O minus. Aromatic primary and secondary amines also react with ethylene oxide, forming the corresponding aryl amino alcohols. Halide addition. Ethylene oxide readily reacts with aqueous solutions of hydrochloric, hydrobromice and hydroiodic acids to form halohydrins. The reaction occurs easier with the last two acids. O plus hydrogen chloride HOCH2CH2Cl. The reaction with these acids competes with the acid-catalyzed hydration of ethylene oxide, therefore, there is always a byproduct of ethylene glycol with an admixture of diethylene glycol. For a cleaner product, the reaction is conducted in the gas phase or in an organic solvent. Ethylene fluorohydrine is obtained differently, by boiling hydrogen fluoride with a 5 to 6% solution of ethylene oxide in diethyl ether. The ether normally has a water content of 1.5–2%. In absence of water, ethylene oxide polymerizes. Halohydrins can also be obtained by passing ethylene oxide through aqueous solutions of metal halides. 2O plus CuCl2 plus 2H2O2 HOCH2CH2Cl plus Cu2 metal. Organic addition. Interaction of ethylene oxide with organomagnesium compounds.
which are Grignard reagents, can be regarded as nucleophilic substitution influenced by carbanion organometallic compounds. The final product of the reaction is a primary alcohol. Similar mechanism is valid for other organometallic compounds, such as alkyl lithium. Other addition reactions: addition of hydrogen cyanide. Ethylene oxide easily reacts with the hydrogen cyanide, forming ethylene cyanohydrine, O plus HCN HO CH2CH2CN. A slightly chilled aqueous solution of calcium cyanide can be used instead of HCN. 2O plus California 2 plus 2H2O2 HO CH2CH2CN plus California 2. Ethylene cyanohydrine easily loses water, producing acrylonitrile. HO CH2CH2CN CH2 equals CHCN plus H2O. Addition of hydrogen sulfide and mercaptans. When reacting with the hydrogen sulfide, ethylene oxide forms 2-mercaptoethanol and thiodiglycol, and with alkyl mercaptans it produces 2-alkyl mercaptoethanol. O plus H2S HO CH2CH2HS2O plus H2S2SO plus RHS HO CH2CH2SR. The excess of ethylene oxide with an aqueous solution of hydrogen sulfide leads to the tris-sulfonyl hydroxide. 3O plus H2S 3S plus O minus. Addition of nitrous and nitric acids. Reaction of ethylene oxide with aqueous solutions of barium nitrite, calcium nitrite, magnesium nitrite, zinc nitrite or sodium nitrite leads to the formation of 2-nitroethanol. 2O plus California 2 plus 2H2O2 HO CH2CH2NO2 plus California 2 with nitric acid. Ethylene oxide forms mono and dinitroglycols. Reaction with compounds containing active methylene groups in the presence of alcoholates. Reactions of ethylene oxide with compounds containing active methylene group leads to the formation of butyrolactones. Alkylation of aromatic compounds. Ethylene oxide enters into the Friedel-Crafts reaction with benzene to form phenethyl alcohol. Styrene can be obtained in one stage if this reaction is conducted at elevated temperatures and pressures, in presence of an aluminosilicate catalyst. Synthesis of crown ethers. A series of polynomial heterocyclic compounds, known as crown ethers, can be synthesized with ethylene oxide. One method is the cationic cyclopolymerization of ethylene oxide, limiting the size of the formed cycle NON to suppress the formation of other linear polymers. The reaction is carried out in a highly dilute solution. Reaction of ethylene oxide with sulfur dioxide in the presence of cesium salts leads to the formation of an 11-membered heterocyclic compound which has the complexing properties of crown ethers. Isomerization. When ethylene oxide is heated to about 400 degrees Celsius, or to 150 to 300 degrees Celsius in the presence of a catalyst, it isomerizes into acetaldehyde. The radical mechanism was proposed by Sidney W. Benson to explain this reaction in the gas phase. It comprises the following stages. 1. OCH2CH2OCH3CHO*, 2. CH3CHO*, CH3 CHO3, CH3CHO*, plus MCH3CHO plus M*. In reaction 3. M refers to the wall of the reaction vessel or to a heterogeneous catalyst. The moiety CH3CHO** represents a short-lived, activated molecule of acetaldehyde. Its excess energy is about 355.6 kJ per mole, which exceeds by 29.3 kJ per mole the binding energy of the C-C bond in acetaldehyde. In absence of a catalyst, the thermal isomerization of ethylene oxide is never selective and apart from acetaldehyde yields significant amount of byproducts. Reduction reaction. Ethylene oxide can be hydrogenated into ethanol in the presence of a catalyst, such as nickel, platinum, palladium, boranes, lithium aluminium hydride and some other hydrides.
Conversely, with some other catalysts, ethylene oxide may be reduced by hydrogen to ethylene with the yield up to 70%. The reduction catalysts include mixtures of zinc dust and acetic acid, of lithium aluminium hydride with titanium trichloride, and of iron chloride with butyllithium in tetrahydrofuran. Oxidation: ethylene oxide can further be oxidized, depending on the conditions, to glycolic acid or carbon dioxide. Deep gas phase reactor oxidation of ethylene oxide at 800-1000 K and a pressure of 0.1-1 MPa yields a complex mixture of products containing O2, H2, CO, CO2, CH4, C2H2, C2H4, C2H6, C3H6, C3H8 and CH3CHO. Dimerization: in the presence of acid catalysts, ethylene oxide dimerizes to a 4-dioxane. The reaction mechanism is as follows. The dimerization reaction is not selective, and there are always byproducts, such as acetaldehyde. The selectivity and speed of dimerization can be increased by adding a catalyst, such as platinum, palladium or iodine with sulfolan. However, 2-methyl-1,3-dioxylane is formed as a side product in the last case. Polymerization: liquid ethylene oxide can form polyethylene glycols. The polymerization can proceed via radical and ionic mechanisms, but only the latter has a wide practical application. Cationic polymerization of ethylene oxide is assisted by protonic acids, Lewis acids, organometallic compounds or more complex reagents. The reaction mechanism is as follows. At the first stage, the catalyst is initiated by alkyl or acyl halogen or by compounds with active hydrogen atoms, usually water, alcohol or glycol. MXM plus ROH MXM RO-H plus. The resulting active complex reacts with ethylene oxide via the SN2 mechanism. O plus MXM RO-H plus OH plus O minus RMXM OH plus O minus RMXM HO CH2 CH2 plus MXM RO minus 2 HO CH2 CH2 plus NO HO CH2 CH2N plus. The chain breaks his HO CH2 CH2N plus MXM RO minus HO CH2 CH2N or plus MXMHNO CH2 CH2 plus MXM RO minus HNO CH equals CH2 plus MXM plus ROH. Anionic polymerization of ethylene oxide is assisted by bases such as alkoxides, hydroxides, carbonates or other compounds of alkali or alkaline earth metals. The reaction mechanism is as follows. O plus Rho Na Rho CH2 CH2O minus Na plus Rho CH2 CH2O minus Na plus NO Rho N CH2 CH2O minus Na plus Rho N CH2 CH2O minus Na plus Rho N CH equals CH2 plus NaOH Rho N CH2 CH2O minus Na plus H2O Rho O plus NaOH. Thermal decomposition: ethylene oxide is relatively stable to heating, in the absence of a catalyst. It does not dissociate up to 300 degrees Celsius, and only above 570 degrees Celsius there is a major exothermic decomposition, which proceeds through the radical mechanism. The first stage involves isomerization, however high temperature accelerates the radical processes. They result in a gas mixture containing acetaldehyde, ethane, ethyl, methane, hydrogen, carbon dioxide, ketene and formaldehyde. High-temperature pyrolysis at elevated pressure in an inert atmosphere leads to a more complex composition of the gas mixture, which also contains acetylene and propane. Contrary to the isomerization, initiation of the chain occurs mainly as follows. OCH2CH2OCH2O plus CH2. When carrying the thermal decomposition of ethylene oxide in the presence of transition metal compounds as catalysts, it is possible not only to reduce its temperature, but also to have ethyl as the main product. That is to reverse the ethylene oxide synthesis reaction. Other reactions, thiocyanate ions or thiourea, transform ethylene oxide into thionous. O plus 2C equals SS plus 2C equals O. Reaction of phosphorus pentachloride with ethylene oxide produces ethylene dichloride. O plus PCl5ClCH2CH2Cl plus POCl3. Other dichloro derivatives of ethylene oxide can be obtained by combined action of sulfuryl chloride and pyridine, and of triphenyl phosphine and carbon tetrachloride. Phosphorus trichloride reacts with ethylene oxide forming chloroethyl esters of phosphorus acid. O plus PCl3ClCH2CH2O PCl22O plus PCl32 PCl3O plus PCl3ClCH2CH2O 3P. The reaction product of ethylene oxide with acyl chlorides in the presence of sodium iodide is a complex iodoethyl ether. O plus RCOCl plus NiRCOCH2CH2I plus NaCl. Heating ethylene oxide to 100 degrees Celsius with carbon dioxide in a nonpolar solvent in the presence of bisnickel results in ethylene carbonate. In industry, a similar reaction is carried out at high pressure and temperature in the presence of quaternary ammonium or phosphonium salts as a catalyst. Reaction of ethylene oxide with formaldehyde at 80 to 150 degrees Celsius in the presence of a catalyst leads to the formation of 1,3-dioxylane. Substituting formaldehyde by other aldehydes or ketones results in a 2-substituted 1,3-dioxylane. Catalytic hydroformylation of ethylene oxide gives hydroxypropanol, which can be hydrogenated to propane 1,3-diol.